All right, let's get started. But before we talk about anything, we have a special guest today from TRIO.
Hi, so I'm just here to tell you really quick about TRIO Student Support Services. We're a program on campus who mostly helps people transfer to universities. So if you're planning on transferring to a university, I encourage you to apply for this program. We have lots of services including academic advising, university tours, tutoring, scholarship assistance, all kinds of things that can help you transfer. So please take advantage of this program. It's really easy to apply. We have a QR code here on the back of this. I'll hand these out. And you can do it on your phone, and we can check on my qualifications for you. So even if you're not sure, you should go ahead and apply, and we can get back to you on that. So if you're planning on transferring, just know that that academic advising part is really, really important, especially if you're trying to go somewhere like with a special plan in order to get your bachelor's degree or beyond. So come and see us just for that. And if you want to get scholarships, scholarship season is coming, so have some people help you out. All of those things can be really beneficial for you. So I'll come pass these around and give you a free pen, and it's totally fine if you want to take it or not take it, that's fine.
Yeah.
If you have any questions, yeah, and if you want to come see us, we're located in the Student Success Center over across the street.
Yeah, highly recommend TRIO. All my students who have been in it, loved it, love the support. I guess they give like a lot of study tips and food too, along with, of course, scholarships like she mentioned. So really great resource for students.
You're in part of it, yeah. You can read that somewhere. All right, thank you everyone. Let us know if you have any questions. You can always come see us over in our student lounge, which is awesome. And thank you for letting me come.
Yeah, thanks so much. All right, so I handed out the wrong homework if you were in lab this morning. So there's the chapter 5 homework. And so yeah, join TRIO if you can. If you're not eligible, right, don't let that discourage you. You can find your own internships, right? Bug me for help. I'm always here as your free resource. And so other announcements, lab, already heard this, but so I did not grade your midterms. I greatly apologize for that. So my 200 level class has about 3 times as many students as we have in here, and they unfortunately sucked up all my grading time. And I did grade like literally all weekend. So I apologize. You guys are next on the list. So now that I have finished my 200 level grading, I will be focusing on your midterm next. And I don't think that anybody, though, is in such a bad position here that we're worried about, like, failing or anything. But like I said, I haven't looked at any midterms, but, I mean, I don't think I need to be concerned about anybody. All right, any other comments, questions, announcements before we keep moving? All right, and we'll probably still do a quiz on Wednesday, just kind of like a little recap, what we've been learning, where we're going. So I'll try to make it easy for us, so I cover the midterm. All right, so let's start with Chapter 5. And so Chapter 5, we're starting to get into reactions, and again, we'll see that today in lab or on Wednesday. And we're getting into moles, so trying to figure out how to quantify things. And okay, so let's just start at the top. So we mentioned, right, this whole physical versus chemical changes. And so we said with physical changes, right, usually it alters the state or appearance, right, but we're not actually rearranging the atoms. And I'll add into this, right, like dissolving something. So if you make a solution of sugar in water or, salt in water, so that would be a physical change, right? So we haven't altered anything by dissolving it. It's still the same chemical, it's just in solution. And so again, right, there's the distinction. So our atoms or molecules, right, do not change their identity during a physical change. So we're not breaking bonds or anything, and this idea will kind of come up again. And so we can think about this with our water boiling, and so we can picture, right, our little water liquid molecules sliding past one another in the liquid state, and then of course, right, we add heat or energy in the form of heat, and then, right, keep adding energy until, of course, they escape. But again, right, we have not broken any bonds here. So that's a good distinction. And so even experienced OChem students will erroneously say, like, breaking bonds, but we're just really disrupting the intermolecular forces. And I'll add that. So disrupt inter, kind of thinking, right, like interstate highway, so intermolecular forces, so between molecules. So again, right, no bond breaking, clear distinction here. And so then we want to start getting into, well, what are chemical changes? And, again, we've kind of been playing with this in lab, so you've seen some chemical changes, right? You did a lab last week on different little reactions and changes. And so, of course, right, the key distinction is that now in our chemical change, our atoms are actually rearranged, and so we get a new substance. And so now we can think about this on the molecular level, what we have seen in real life. So of course you can have this iron nail, and it obviously starts off as a nice piece of shiny iron. You can again think of it molecularly, so all these irons in this repeating pattern here. And then of course, right, over time, oxygen comes along, and then, right, you can see a new structure. So it starts, right, rearranging the iron, forming the new iron 3 oxide crystals, and then obviously, right, that changes its composition. And then you can say, okay, well now the iron is kind of crumbly, and so now it loses, right, its solid integrity. So all these things are changing our iron. And so again, right, we have a new compound. And so your lab last week gave you a really good sense of this, right? So then we had to figure out, well, how do we write our reactions? And again, this is really important in chemistry. Like if you were in grad school, every day you're writing your reaction or reactions of the day, kind of mapping out what you're expecting. And there's a lot of information, right, in this little statement. So of course we have reactants on the left side, so whatever our starting materials are. So I'll put starting materials. Sometimes we call them reagents as well. And so the other thing with this reactants, and just kind of thinking about like how to write chemical equations, what are we doing, is it always has to be something that's, I like to call a bottle, like something in a bottle, right? So that you could purchase it from Sigma Aldrich or whatever chemical supplier, Flynn. You can buy it, you can purchase it in a bottle. Okay, I can react this. And then of course our products are on the right. So now, right, they're telling us what we maybe expect to happen or what we, have known to happen from previous reactions of this. And so then we want to focus on writing our chemical formulas properly. So going back to all those basics, right, of writing ionic compound names, balancing out the charges, all that good stuff. And so then, right, we see, again, all the details. So it states our quantities. And so again, right, we've kind of seen this. So we can use, right, our coefficients to balance. So this is not balanced. So we could write A2 here, let's see, and A2 there. So now that looks balanced, right? So now we have our ratio of our quantities. So 1 to 2 to 1 to 2 ratio. And then we also want to put the states, so they're physical states. And so that means, right, again, how are you adding it? So in this case, we're saying, okay, well, we have two gaseous reactants, right? And that's also telling you, well, that's going to be kind of tricky. How are you going to add those two gases? Is it going to be like maybe we saw in the balloon demo where you already have these two gases loaded up in a balloon, and then you react them? You have to think about all those kind of physical limitations. And so that's what you want to get from this information. So we have G for gas, L for liquid, S if something is a solid, and then don't forget that little AQ, which means, right, aqueous solution. So basically, right, something dissolved in water, and sometimes there's some sort of concentration, like 1 molar, so some sort of concentration value. So again, right, you've kind of seen that in lab, like you reacted your 1 molar of HCl with your magnesium, and you could write that out, write your magnesium. Actually, let's just draw that. So a quick example. So, right, we had our magnesium in lab. So we'll put a solid, right, because we added a solid piece of magnesium. And then plus, HCl. And then gives us, so H2 plus magnesium chloride. And again, right, you can put your states. So our HCl was aqueous, right? H2 we would expect to be a gas, and you saw bubbling. And then our magnesium chloride, if it's just dissolved in solution, then it's aqueous. And so that's just an example, and then of course, right, we want to balance it. And so again, right, I've written out all our formulas, making sure we write out magnesium chloride, right, balancing out those charges. And so now we can balance it, so 2 there, 2, and so now we're balanced. And so again, right, a lot of information in this little chemical equation. So that's why I'm saying, right, super important. Again, you have all this information in there. So, right, we have our formulas of our reactants and products. And I'll add again, right, so make sure your formula is correct. Make sure your starting formulas are correct. All right, it's really hard to balance your equation if you don't have, obviously, your formulas written correctly. And then, okay, we have our formulas. like we mentioned, okay, we state our states of matter, solid, liquid, gas, aqueous. And then again, right, we get our relative amounts, so they're ratios. So we're getting there, right, this mole-mole ratio idea. And then from there, we can use all that information to determine the relative weights of our reactants and products used. And again, right, you're getting a taste for that in lab this week. And so now we're getting into the kind of, right, the bulk, the chemistry. And so again, right, if you're a chemist, you're a working chemist, you're going to be doing this like literally all day, every day. And that, right, you have to figure out, well, how much product am I going to be making? How much do I expect from my reaction? And so, of course, right, this goes back to our law of conservation of mass. So, right, we said, well, matter is neither created nor destroyed. So again, just going back to that concept of atoms being rearranged, right? So we need to account for all of these atoms in our equations. We need to show, where they went. And then you've already kind of started practicing the balancing equations, right? But then you just kind of go back and forth, play with it a little, and use your coefficients to balance out your equation. And then, so the fancy word for all of this in chemistry is called stoichiometry. Since again, it's so important that's literally what a big part of chemistry is, right? How much can I make from my starting materials? How much do I expect? And reporting yields, all that's really important. And so we'll be diving into that officially. And so again, right, emphasizing, well, we have to start off with our balanced equation, just counting up our atoms like we've done. So, right, 1 carbon, 4 oxygen atoms, and then 1, 2, 3, 4 hydrogens, 1, 2, 3, 4 hydrogens. All right, so now we get to our stoichiometry. And so if you like cooking, stoichiometry should be relatively simple. And so again, right, our coefficients specify our relative amounts. So again, it's just like a ratio. So now we're saying, okay, we have 2 equivalents of octane are burned with 25 equivalents of O2 to give us 16 equivalents of CO2 and 18 equivalents of water. So this could just be like a cookie recipe, right? Like a good batter recipe is always 1:1, flour to sugar, and then, 0.25 of egg or whatever your stoichiometry is for your equation. And so we can also be talking about, individual molecules. So we could say, well, 2 molecules react with 25 molecules of O2 to form 16 molecules of CO2 and 18 molecules of water. Or we could also translate this to moles. And so we'll keep talking about moles. We'll define that, what it is in a second. But again, our mole is just basically our normal unit, right? So kind of our macroscopic unit, so we can quantify these things in terms that are reasonable. And then, not only that, but of course can scale by any factor. So you could do this, times 2. Hey, I want to double my cookie recipe. So then, then it'll be a 4 moles of octane to 50 moles of oxygen to give us 32 moles of CO2, and 36 moles of H2O. So we could scale it by any factor, You could scale it by 100, doesn't matter. So that's kind of the point, They're proportional. We can scale it up and down as we need. So we can, of course, make the appropriate amount. All right, so let's look at our cooking analogy. And so now we have this stoichiometry. So our pizzas depends on, of course, right, the amount of ingredients we have. So we have our official pizza recipe here. So we have, right, 1 crust goes with 5 ounces of tomato sauce, 2 cups of cheese to give us 1 pizza, right, as our product. So then we can set up our dimensional analysis, our stoichiometry, and so now look at what we're doing. So of course, right, this is our balanced equation. So this is always, right, our reference here. So anytime we're trying to do any mole-mole ratio comparisons, we always have to refer back to our balanced equation. And so then we can set up our dimensional analysis. So then it's asking, okay, well, how much pizza can we make then if we have 10 cups of cheese? And so then they've shown it here, but right, we're going to go back to our balanced equation. Okay, well, I see I need 2 cups of cheese for every 1 pizza. And so this is, I like to call this, right, almost our conversion factor from our balanced equation. So as long as you can remember where this comes from, you'll be fine. And then, of course, unit canceling, right? So cups of cheese cancels. We want pizza on top. So now, okay, we can say 10 cups of cheese will give us 5 pizzas. All right, so let's keep practicing with that. And so let's make some s'mores here. So we have to start off with our balanced equation. And so we can make our s'mores. So right, we need 2 graham crackers. And then let's put in there our 1 jumbo marshmallow. I apologize for my artistic skills. So 1 jumbo marshmallow. And then we'll do plus 3 pieces of chocolate here. And of course, this gives us, right, 1 s'more. And so let's see. Let's just say, so our class is roughly 20 people. So how much of each ingredient do I need? All right, so go ahead and figure out how to solve that. So what do we get?
Got
Okay, so 40 graham crackers to 60,
No, I said to 20. To 20, and then the
Oh,
next one was 60.
sorry.
40, 20, 60 equals 20.
Excellent. And so, right, take a second though to kind of slow down what happened at each step. So, right, and that's kind of what we're talking about s'mores right now. It's like everybody likes s'mores. It's easy to kind of see the math right now, so we're feeling good. And yeah, we're trying to get to 20 s'mores. And so, right, you can see that you just kind of did a ratio at each point. So if we want to make one s'more, that requires 3 pieces of chocolate. So if we want 20 s'mores, right, we have to set up our relationship for each one. So I'm just showing the work for chocolate here. Again, just so you can see the math, so that when we do chemistry stuff, we won't forget. And so yes, that's how we got the 60 pieces of chocolate. And then I don't know if anybody else needs to see the rest in explicit detail or. All right, so now let's try another type of problem. And so we'll have these kind of limiting reagent problems. And so let's see how this problem may go. And so now we say, if I have 77 graham crackers and excess marshmallows and chocolate, so now we're asking how many s'mores. Do we have an answer for this one?
Yeah, I don't have an answer. I'm just asking, what is that word for marshmallows? I can't really make it out.
Excess?
Oh, excess.
So what do we get for this one? Yeah. So 38, so that sounds good. And so again, right, mathematically, this is probably easy to see, but we can still write it out. So 77 graham crackers, and then, right, we have our conversion factor. Well, I know that 1 s'more takes 2 graham crackers. And so, yes, you should get about 38.5, or of course, right, 38 whole s'mores. All right, so let's try now a slightly more involved problem. And so sometimes you have these more involved limiting reagent problems. And so now we say, well, if I have 321 chocolate pieces and 178 graham crackers. And we'll have excess marshmallows. So now how many s'mores can I make? Oh, you're fast. We'll let other people catch up to you. So how do we do this problem? So I see a few answers. So what do we have to do?
I did the math on both, and then just see which one sounds.
So exactly, right? So unfortunately, there's no quick shortcuts, right? We have to literally do the math on both. And so, okay, let's compare the chocolate pieces. And so this looking sounds like the chat also has the same conclusions as y'all. So again, I'm just setting up our proportions here. So again, this is pulled from our balanced equation. Seems pretty easy right now. Don't let funky numbers confuse you later, is my only word of advice. And so we probably got 107 s'mores with these chocolate pieces. And then looking at our graham crackers. So 178, and then divided by 2 graham crackers. And then you compare these two. So of course you have to pick the least one, right? Because that's the one that's going to run out first. So now we can say, okay, this is how many I can make, so 89 s'mores. And then we can use this term, limiting reagent. So that means that our graham cracker, right, is our limiting reagent since it's going to run out first. So it's the smallest amount. So, okay, that's my limiting reagent. I can only make 89 s'mores because of my graham crackers. All right, so we're feeling okay right now, I'm sure. So let's take it to the slightly next level. Again, we're comparing our graham cracker math to our mole math. And so obviously, right, all your compounds have a molecular weight. So let's make that same, again, analogy. So I'm just going to rewrite our balanced equation for a second. And then, so of course, right, normally you would add up all your atoms, right, to get the molecular weight of each compound. But I will give you our molecular weights. So our molecular weight of our graham cracker is 55 grams per mole. Our jumbo marshmallow is 70 grams per mole. And our chocolate pieces are 15 grams per mole. And so let's just start off with doing our first easy right stoichiometric relationship. So what is the mass of one s'more then? So how do you determine that? What do we get for our mass? I would double check the answer in the chat. Got a different answer. What did you get, Isaiah? So 225, that's what I got. And, oh, guess it was typo. So, right, you have to multiply this times 2. So let me fire up my calculator. So 2 times, right, our molecular weight, so 55, plus our jumbo marshmallow, plus 3 times 15. So yes, 225, right? And again, that goes back to our law of conservation of mass. Of course, all our reactants have to equal, right, our product mass, so they didn't just disappear, they became something. All right, so now let's get into kind of more difficult calculations like we might see, again, with chemicals. And so now if I have 777 grams of graham crackers, now how many s'mores? So see if you can figure out. So kind of walk me through what you're thinking. What do we have to do first with this problem? Yeah.
Divide the grams by the weight of 2 grams.
Or you mean like the mass of one? Yeah, because I wouldn't want to do two, just because that gets like confusing.
Right.
Yeah, because we could talk about mass balancing, but I'll kind of put that thought to the side unless like someone wants to do that, and we'll focus on moles. So yeah, just divide it by the one amount. So this is the same thing as, right, dividing your, whatever your amount of product you have. So if you're in lab, right, what you were trying to do, okay, if you have your magnesium sulfate, your anhydrous, so dividing by your molecular weight, that's essentially what we're doing here. So dividing by, right, our molecular weight of graham crackers. And so, again, you can practice your units with this one. So we said, okay, well, 1 mole of graham cracker is 55 grams, right? 55 grams per mole. And so then what do we do from here? So I'm just kind of setting up the dimensional analysis. So now we have essentially, right, our moles of graham cracker from this. And then how do we figure out s'mores, though? Exactly. So, right, divided by 2, but what we're really doing is, okay, we're going back to our balanced equation and checking out our ratio, right? And then, okay, well, now I need 1 s'more on top. We're going to cancel out graham cracker. And so now we can multiply across. So again, right, we're doing our first portion, so just solving for moles. And then doing our ratio, right? And so then how many s'mores do we get from this? 7. So 7, and Chet agrees. Punch that out as well. So again, dividing by our molecular weight gives us moles, and then, oops, I put 1 there, sorry. And divided by 2. So now we're at 7. Excellent. All right, let's try the next level of question, right? So now those limiting reagent problems, but like you'll see with chemicals, you'll have 2 different, right, gram amounts of something. So now let's try. So if I have 420 grams of marshmallows, and 334 grams of chocolate. And of course, right, excess of our marshmallows, how many s'mores? So I'll just kind of put this setup, right? So like we mentioned, well, we have to unfortunately do the problem twice, essentially. And so we could start off with our marshmallow calculation. So beginning with our amount, right? So how much we have. And then, okay, well, let's figure out how many moles that is, since we need to compare mole-mole ratios. So dividing, right, by the molecular weight of our marshmallows. And then going back to our equation. So 1 marshmallow is required for every s'more. So how many s'mores did you get out of these 420 marshmallows? 6. I have that in the chat as well. So 6 s'mores. And okay, let's repeat that calculation with our chocolates. So again, similar setup. So what we started with, 334 grams of chocolate. Converting to moles, so 1 mole is 15 grams. And then again, write our mole-mole ratio from our equation. So 1 s'more requires 3 chocolates. So then how many s'mores do we get from these chocolates? So 7. So then which one is our limiting reagent? Marshmallows. So marshmallows, again, fewer. So, okay, limiting reagent. Questions on this one? All right, we'll do one more little practice, then we'll take our break, and then we'll switch gears to real chemistry. And so the last type of question that we'll kind of see is this percent yield thing, and it could be worded in different ways, but let's just look at some concept. And so it could be something where you have to calculate, of course, the yield. But let's just say, okay, we expected to make 60 s'mores. And again, right, this could have been ascertained from other problems. Okay, so we expect 60 s'mores, again, from all our reagents that we have. And then it says, however, we got too hungry and only made 56 s'mores. So what is the percent yield? And we'll just go over this one. And so percent yield is just defined as our actual, right? So what we actually have in hand. So especially, you know, thinking of chemistry, and all sorts of things can go wrong, right? Your product can fly away at the end. But okay, however much we have actually in our hands versus what we theoretically calculated. And so that's the other thing I want to emphasize, right? Every time we do these stoichiometry equations, that's your theoretical yield. So that's how much you expect, right? 100% yield, everything is going great. And then, of course, times it by 100 to get it in a percentage. And so for this example, again, pretty simple now. Okay, well, we actually had in hand 56 s'mores. We expected 60. So now we can get our percent yield. So 56 divided by 60. So about 93% yield. And so this would be a pretty good yield for like CHEM. And so the other thing to think about and is just kind of, well, what does this mean to our yield and why do we care? And, you know, we may not care so much because usually we're just doing single step synthesis, but you have to think about, right, in the research setting, and let's just take a really small synthesis. So let's just say, well, what if we have a 7-step synthesis, right? And then at each step, right? Let's just say we have a 93% yield. However, right, what's your final yield at the end of that 7 steps? And so how you would determine that is, right, you just start multiplying each percent yield, right? So you can think about it, well, if I have a 93% yield in one step times a 93% yield in my second step, and so basically it ends up being our 0.93 to the 7th power, right? So however many steps you have. So number of synthetic steps. And so, okay, this great 93% yield that we just determined. So 93, take that to this power of 7, right? So doing that 7 times, and again, that's pretty optimistic. And then we can see, well, by the end of that, for our 93% yield on a 7-step synthesis is already cut down to 60, right? So now that's 60% after 7 steps. And so I don't know how much necessarily I'll test you on this specifically, but right, this is just something to think about why yield is so important, especially at every step. You know, you're talking about reagents being lost at every step, even though, again, right, over 90 is considered like a good yield for an organic reaction, but it's still, you know, quite a process. And that being said, like a 7-step synthesis is pretty small, so like, especially these total product synthesis, I mean, they could be 20 plus steps. So, you know, if once you're at that level, obviously, right, that's why you want it to optimize every step. So just kind of something to think about. All right, let's go ahead. We'll take our little break and then we'll practice some more stoichiometry. So we'll actually do chemistry. But hopefully, since you all did so well with the s'mores, you can just translate that over to chemistry. All right, take a little break. I'm going to try to print out some stuff for you too. So we'll be back at like 2:05. Oh, you can just make a file. All right, let's start getting back into it. So make sure you pick up the mole highway. I printed that out for you. And so this is just a nice little sanity check and kind of cheat sheet reminder to help you. And so we have, right, moles in the center. So this is kind of, I would consider this our safe space for chemistry. So if we're at moles, right, that's always a good place to be. And so it tells you how to go back and forth. So of course, right, we have our dimensional analysis, but again, you might just like this as an extra guide. So it's telling you to go from mass to moles, right, divide by the molecular weight, moles to mass, multiply by molecular weight, and then we'll talk about this particles. Essentially, this is just another conversion factor, though, or we can say 1 mole is equal to 6.022 times 10 to the 23rd, and that's atoms or molecules or things. So you could have, right, a mole of donuts, so that would be 6.022 times 10 to the 23rd donuts. So just kind of like a baker's dozen unit. So you'll probably see practice problems using this Avogadro's number, so we'll kind of practice those. And so, right, this is just your mole-mole ratio. And then this little bit over here with the volume has to deal with density. So if you were like trying to figure out the volume amount of some liquid, so this would be a pure substance. And then you'd have to get the density of that substance. So I'll try to practice one like that, but you probably won't see too much of this. And then later we'll see kind of a different volume stoichiometry with concentration and molarity. All right, so hopefully we're feeling pretty good after we did those marshmallows. And so again, now we're just gonna get rid of the wonderful tasty marshmallows and instead talk about chemicals. And so again, right, it's just telling us our ratio relationship. And so these I would consider all these, right, are again our conversion factors from our balanced equation. So just our relationships of all, right, our reagents and products. So we can, of course, relate, right, our octane to water or oxygen to CO2, right? It doesn't matter. All that is in there. All right, so now let's try this practice problem. So how many moles of CO2 are formed if 22 moles of octane are combusted. So go ahead and try that, and then we'll scroll down. Just remember, this is just like our s'mores. So do we get an answer for this one? Yeah. 88. I double check that. So let's start highlighting. So what do we need to look at, right? So we have 22 moles of octane, and we're trying to figure out CO2. So, right, highlight what we're comparing. Okay, well, we have 2 moles of octane, gives us 16 moles of CO2. And well, as I scroll down, I kind of reveal their work. But, right, let me go ahead and set up the same thing. So what we're going for, again, we started with 22 moles of our octane. And then all they've done in this second step, right, is take their conversion factor. Well, I'm trying to get CO2, so my 16 moles of CO2 goes on top, my 2 octane on bottom. And if you would simplify this to 8/1, that would also be fine. And so then now multiply across. So 22 times 16 divided by 2. And we should get 176, which is, you question yourself. And so, right, so make sure that you're understanding where this is coming from, because this is really your most important factor, right? This little conversion factor relating the two. So it was super easy before with our s'mores, right? Everything was just a 1 to something ratio. But don't let the different numbers confuse you. So we haven't done anything different. All right, so we got our 176 moles. And so again, like we saw in our little happy s'mores, we usually have to go from mass to moles, and then, right, using their ratio, or what I'm calling, right, our conversion factor, essentially, and then back to moles, back to mass. And so this is essentially, right, the whole bit of stoichiometry just kind of written out in symbols, right? So you're starting with however much amount of something, You're going to be determining the moles, right? Dividing by molecular weight. Then that gives us to our ratio, right? Your balanced equation. So you can, again, get to your safe space, compare your ratios. Then that gives us moles of whatever we're desired quantity we're looking at. And then we can go from moles back to mass. And so again, right, this looks hopefully not too scary, but it's just what we've been doing with our s'mores. So now, see if you can start this problem. So again, we have our balanced equation. So what is our mass of carbon dioxide produced when 3.6 times 10 to the 15 grams of octane is burned and we have excess oxygen? So see if you can start that problem. So what information do we need to maybe calculate? What do we have? So what do we do? We have this 3.6 times 10 to the 15 grams of octane, and then what do we do with that?
You have to determine the mass of CO2, and I can't
Oh,
remember what it's called.
octane.
There we go, octane, right?
Yeah, so let's get those molecular weights, right? So eventually we will need the CO2 molecular weight, and then we need our octane molecular weight. So we could, right, add that from our periodic table. So we have 8 times 12.01 for carbon, or again, slight variations with rounding, plus 18 times 1.008 for hydrogen. And so it gets somewhere around 114.22. Again, right, your number could vary slightly. I'll just use that, so 224 grams per mole. And then what's the molecular weight of CO2 while we're at it?
About 44.
44 sounds good. I got that as well. So 44 grams per mole for CO2. All right. So now we can set up, or at least start setting up our dimensional analysis. So we start, sorry, I lost my page there. So start with our grams of octane, so 3.6 times 10 to the 15, so grams of C8H18. And so again, just like we did with the s'mores, when we have our mass amount, we need to divide it by our molecular weight to get to moles. So 1 mole of octane was what we calculated, so that 114 roughly. All right, so then that gives us moles of octane. And so the next step, right, is our mole-mole ratio. So we have octane to CO2. So now we can set that up. So again, CO2 is on top, 2 moles of octane on bottom. So you can follow your dimensional analysis. So grams cancels, now moles cancels of octanes. Now we have moles of CO2. And it asks us the mass of CO2. So then our last step, right, is multiplying now by the molecular weight of CO2. So 44 grams for 1 mole of CO2. All right, so there's our setup. And so now we can punch this in. So you can either multiply, again, straight across, or I like to do just step by step, just kind of check myself. So take my grams, divide it by, my molecular weight. All right, so that gives us 3 times 10 to the 13, moles. Then times, so 16 over 2, so I'm just going to multiply by 8. And then multiply by 44 to get our mass. And so then we get roughly 1.1 times 10 to the 16 grams of CO2. So did we all get this answer? Right, so don't let the big numbers intimidate you. So again, everybody was doing so well with the s'mores, but suddenly we put funky numbers and chemicals and everybody forgot everything. Questions on this one? All right, so try this next problem. So magnesium hydroxide is the active ingredient in milk of magnesia, and it neutralizes our stomach acid, which can be primarily described as hydrochloric acid. And so they gave you the neutralization reaction. So magnesium hydroxide plus 2 equivalents of acid gives us 2 equivalents of water and magnesium chloride. So then see if you can figure out our mass of HCl if we are neutralizing a dose of milk of magnesia containing 3.26 grams of magnesium hydroxide. So start piecing together too, like what other little bits of information do you need to solve this? What do you need to calculate? The equation's already balanced, but that's always, right, your first step is, do I have a balanced equation? So then start walking me through, so what do we have to do for this problem? So what information do we need? So what information did we have with the s'mores that we didn't need to calculate that we need to do here? Crystal, what did you do?
I'm not sure this is correct, but I put two, of the hydrochloride over the, I think that's a conversion factor.
So that's our mole conversion factor, right? So we can say, okay, what's our mass of HCl? So we have something, right? Well, 2 moles of HCl for every 1 mole of magnesium hydroxide. Okay, but then how do we get to moles? Because we have this, but we're starting with 3.26 grams of magnesium hydroxide. So what do we need to calculate? Yeah, Jen? So we will need the HCl mass probably at the end. But yeah, we'll want to start with this mass. So right, not wrong to calculate that. So what is the mass of HCl? So 37.4 grams. Is it 37 or 36? Sorry, when you've been doing chemistry as long as I have, I've memorized like certain molecular weights, so. Yeah, but I would put in 35.45 and then plus the 1, right? Oh, but there's only 1 HCl in the formula, yeah. So it should be 35.45 plus our hydrogen mass, so something like 36.458. So grams per mole. And then we still need our molecular weight of magnesium hydroxide. So don't forget that OH, you have to do 2 of them. What do we get for the mass? So 58.319, you said? That's what I have written down in my notes. So did we get about this for our molecular weight? Oh, sorry, I drew the wrong arrow. For our magnesium hydroxide, so 58.319 or so grams per mole for magnesium hydroxide. All right, so now we can start setting more things up. So we started with our 3.26 grams of magnesium hydroxide. All right, and then divided by the molecular weight. So 1 mole of magnesium hydroxide is 58.319 grams or so. And again, we can go step by step. Maybe that makes more sense to people. So then we figured out we got 0.0558 moles of magnesium hydroxide. So then that's where our mole ratio comes into play that we already picked out, right? 2 to 1. Again, just looking at our balanced equation, so times 2. So that gives us moles of HCl. And then, of course, right, the last bit, if we want to go from moles to mass, so then we can multiply it by 36.458, so grams per 1 mole of HCl. And so we should get about 4.08 grams or so. Questions on this one? So let's try another one. So let's look at this ammonia reaction. So ammonia, although I don't think it's typically synthesized this manner, it's usually synthesized in the H2 plus N2 method. But you can also use 2 equivalents of NO plus 5 equivalents of H2 to give us ammonia, and water. And so now it says, so starting with 86.3 grams of NO and 25.6 grams of H2, so find our theoretical yield. So how would you approach that? So what do we have to do to approach this one? So walk me through what we did. Yeah. So you actually want to calculate them separately. So like each theoretical yield and then figure out which one is the less. Yeah, so that was kind of the first trick, is identify, well, what type of problem is this, right? And so this is a limiting reagent problem, right? Since we're given two amounts, but we don't know how much they create. So we have to first determine that, right? So basically we have to do the stoichiometry with the NO first, figure out, right, how many equivalents this 86.3 grams makes of ammonia, and then repeat that calculation with H2. So let's start that with NO. And so what's our first step here to figuring out how much ammonia we can get? What did you say? So what's the mass of NO? 30.006 grams or so. And so then, right, we can find moles. So we have 86.3 grams of NO divided by the molecular weight. So 1 mole of NO was 30, we said. All right. And then from there, what do we do? Yeah, the ammonia, you mean? So next, right, we have to compare our mole-mole ratios, right? So we have moles. So again, you really have to think about what's happening at every step. And for some reason, the s'mores just are so much easier, right? So now we have moles of NO from this calculation. And okay, but we're still trying to get to ammonia. So that's where, right, we go back to like our happy s'mores. So our graham cracker to s'more ratio. And so now we're looking at our NO to ammonia ratio. And they are a 2 to 2. So you could just, simplify this 1 to 1. Not a big deal. And kind of ignore that. Okay, so right now we have moles of ammonia, which again is equal to the moles of NO in this case. And so then the last step is we need to find our yield, and it's asking for it in grams. So we need to multiply by the molecular weight of ammonia. So what's the molecular weight of ammonia? Double check that, because 1 nitrogen, 3 hydrogens. Yeah, so about 17. And so now we can multiply it, so 17 grams, or 17.031 grams per 1 mole of ammonia. And so now we finally gives us grams of ammonia. So now I'm just going to punch this in. And so again, right, just sanity check, what are we doing? Okay, we first determined moles of NO. We got 2.87 moles, 1 to 1 ratio. That's our moles of ammonia. So times 17. And so we should get like 48.9 grams of ammonia for the first one. All right, so take a minute or two. So see if you can repeat that for H2, so fix your calculation if you need to. Don't forget H2 is diatomic now in this case, since you're talking about your reagent, H2. So then we can start walking through the calculation. So now just repeating it, right, with H2. And so now we're starting with 25.6 grams of hydrogen. And then divided by, so 1 mole of H2 is, of course, what, 2.016 grams. And so, okay, now, right, we're at moles of H2. Go to our balanced equation here. So, okay, now we have a 5-to-2 ratio. So a little trickier. And so again now, oh, what happened? So our 2 moles of ammonia goes on top. 5 moles of H2 on bottom, right? Since we're trying to get to ammonia on top, canceling out H2. And then just like our above calculations, and then we need to multiply this by the mass of ammonia. So our 17.13 grams per 1 mole of ammonia. And so what do we get for this? And so now I get 86 grams for our ammonia. So is that what everybody else got as well? Just double check me on that one. And so, right, so again, this is our theoretical yield, so 86.3. But now which one is smaller? So which was the least amount? So the NO, right? So now we have to look at them and, okay, well, the NO was the least amount. And so this means, right, that this is our limiting reagent then. And then this would be the correct, right, theoretical yield then. Since we are, again, limited by our limiting reagent, so this is the max we can make, again, until our reagents run out. All right, that's a good place to stop for today. So probably on Wednesday, we'll just do some more practice problems, kind of from the homework, looking at those, especially with like the atoms and molecule weird ones. And maybe we'll try to do chapter 6 as well. Just looking ahead to next week, since don't forget, we do have Monday off, so we are losing a day, but I'll make an announcement about that. All right, see you all on Wednesday.
Did you say there was gonna be a quiz this Wednesday?
That's my plan, yeah.
On over what?
Just like, you know, the stuff we had on our midterm, whatever, chapter 4 stuff.
Oh, just chapter 4, or everything we went over our midterm?
I mean, probably more like chapter 4 focus, geometries and stuff, and shapes.
Is there any chance I could get my lab back from today just for help with homework?
Oh, yeah.
Sorry. Thank you.
Yeah.
Is there a chance I can just do a quiz today then? It's just review over chapter 4.
Let me look.
Otherwise, I can just do it